Hi everyone, Ross Satchell from Microchip back again. Welcome to episode 15 in our AVR Bare Metal series. This is the final video in the series. In the previous video, we went over the final project host implementation. In this video, we will cover the client device implementation, test everything including the current consumption. We will also cover some gotchas encountered while building this project. So let's get started. Create a new project and include the libraries that we will be using. We will need the delay library and the interrupt library. We also have to define the fCPU macro. Since we will be mostly using a 32.768 kHz clock, we will use that here. Then we will include the following libraries that we have created: main clock control, ports, sleep, SPI 0, and USART 0. Next, we need to define the number of bytes that the client device will receive. Recall from the last episode that the host was sending 2 bytes, so that is the number of bytes that we will be receiving. Then we have an externally declared variable, which is the SPI data array, which has a size of 2 from the define above. Next, just like we did for the host device, we create an enum of the different states that will be used. So we have init, switch to high-speed clock, receive SPI, switch to low power clock, write to USART, and sleep. Then just as we did for the host device, we wrap our states in a struct so that we can use dot notation. Now for the main function. We create an instance of the state machine and set its initial state. Now we enter the while loop. Just like for the host device, we have a switch case statement. The first state is init. The first function is port init. So let's control-click to follow to the definition. Port C and D have all pins set to outputs. Port F has only pin PF5 set as an output. Port A has pin 5 set as an output, while pins 4, 6, and 7 are all inputs. Then just as we did with the host device, we use the port pin config register to disable inputs and enable pull-up resistors. Next, using the pin control update register, we copy those settings to port A, pin 0 to 3, then all pins on port C and port F. On port D, we copy those settings to all pins except pin PD4, which will be used by the USART. Next, we tie all unused pins high. Then finally, we set pin PA7 interrupt for a falling edge and enable its pull-up. While we're in the ports.c file, let's take a look at the other useful things there. Firstly, near the top of the file, we have a volatile, unsigned 8-bit integer variable called client select pulled low flag. This is a software flag that will be used to indicate that the host device has pulled the client's SS line low, which is the first thing to happen in an SPI transfer. After the port init function, we have another function called getClientSelectFlagStatus, which takes no parameters and has an unsigned 8-bit integer return. In the function, it simply returns the volatile variable clientSelectPulledLow flag. Next is a function called clearClientSelectFlag, which takes no parameters and has a void return. It simply clears the clientSelectPulledLow flag variable by setting it to 0. Next, we have the ISR, or interrupt service routine, for the port A interrupt vector. In the ISR, the first thing is to determine whether pin 7 was the source of the interrupt. If that is the case, we clear the interrupt flag in the intFlags register, and we set the client select pulled low flag to 1 so that it can be processed in our main function. Now let's return to the main.c file. Next, we call the low power clock control function just as we did with the host device. Then we call the USART init function, and initialize it for a baud rate of 1200, asynchronous mode, no parity, 1 stop bit, and 8 data bits. If you're unsure about this implementation, please revisit episode 8 in this series. Then we have a function called SPI Client Init. So let's control-click to follow it. Its initialization is somewhat similar to the SPI Host Init function, except that we set this device as a client. Then we enable the SPI Interrupt Enable and the SPI Receive Complete Interrupt Enable. Finally, we enable the SPI peripheral. Next, we call the Sleep Init function, just like we did for the host device. Then we enable global interrupts. Finally, we set the next state to be sleep. In the sleep state, the first thing is a sleep instruction. The CPU will remain there until woken by the pin change interrupt for pin PA7, which is the client select or SS line for the SPI bus. When the pin change interrupt on pin PA7 fires and sets the client select pulled low flag variable, we check that using the getClientSelectFlag status function. If that returns a 1, then we call the clearClientSelectFlag function that resets the client select pulled low flag variable to 0. Finally, the state machine state is updated to switch to high-speed clock. Now we progress to the next state, switch to high-speed clock. In it, we call the main clock control function, where we select the high-frequency internal oscillator, OSC-HF, and set the CPU frequency to 4 MHz. Finally, we update the state to receive SPI. In the receive SPI state, we have a while loop that checks the return of a function called getPacketCompleteStatus. So let's control-click to follow to the function definition. We can see that the function takes no parameters and has an unsigned 8-bit integer return, and it simply returns a variable called packetComplete. If we scroll to the top of the file, we can see 2 volatile unsigned 8-bit integer variables, one called dataIndex and the other is packetComplete. Scrolling back down, we have another function called clearPacketCompleteStatus, which simply resets the packetComplete variable to 0. Then under that, we have the ISR. We start with an if statement where we check the SPI int flags register for the SPI receive complete interrupt flag. If that has been set, we read the received byte into the SPI data array, and we then post increment the data index variable. If the data index variable is 2, meaning that we have received 2 bytes, then we reset the data index variable to 0, ready for our next SPI data transmission. Finally, we set the packet complete variable to 1 for processing in our state machine. Returning now to the main.c file. So the while loop sits until the SPI packet is complete. We then call the clearPacketCompleteStatus function to reset the packet complete variable and set the new state to switch to low power clock. In the switch to low power clock state, we call the low power clock control function where we select the 32.768 kHz internal oscillator and set the next state to write to USART. In the write to USART state, we first print out the 2 received bytes. We then create an unsigned 16-bit variable called results, and we write SPI byte 1 to the high byte of results variable, and we write SPI byte 0 to the low byte of results variable. We then print the results variable as a sanity check. Recall that the most significant bit in the high byte contains the window compare result, and we can isolate that by simply bit shifting the results variable to the right 15 places. Next, we isolate the ADC results from the results variable by bitwise ANDing the results variable with hex FFF, which is a 12-bit value just like the ADC result. We then print both the window comparison result and the ADC result to the terminal. Then add a delay to ensure it completes the printf operation before we set the new state to sleep and power down the CPU. And that's it for the client device code. Let's program both host and client devices and test it. Now I will first connect my power debugger to the host device and set the output voltage to 3.3 volts. And I also have a USB phone charger powering the client device. Upon startup, we can see the host is consuming about 6 microamps. Now let's press the button and we see firstly the current increase to about 160 microamps while taking the ADC measurement, and then spike to about 1.3 milliamps during the SPI transfer. After the transfer, the host returns to sleep and consumes about 5 microamps. Now, while looking at the logic analyzer, I will press the button to take one measurement well below the ADC window, a second measurement inside the window, and a third measurement well above the window. We can see the data trace as well as the terminal output where the raw SPI data is printed. The entire 16-bit results variable is printed. Then the window result and ADC result are printed. Now some portion of this sleep current measured is due to the logic analyzer being connected. So let's disconnect the SPI pins from the logic analyzer and just leave the USART connection. Now we can see the host device consumes about 1.5 microamps. Now let's connect the power debugger to the client device. While it is asleep, it consumes about 2 microamps. When it receives SPI data and writes to the USART, it consumes about 1.1 milliamps before returning to sleep and again consuming about 2 microamps. Now let's cover some gotchas encountered while building the final project. There are 2 main ones that I want to talk about. Gotcha number 1. Originally, when switching between the high-speed clock and the low-power clock, I redefined the fCPU macro, which is used for delays. However, I found that sometimes, but not always, the compiler would optimize out the extra defiance of fCPU. This meant that the delay used between pulling the SPI client select line low and sending the block of SPI data would be greatly shortened, resulting in the client not being ready in time for the data block. The solution to gotcha number 1? I created a spin lock function in the host implementation. The function took one parameter, an unsigned 16-bit integer called time in milliseconds, and has a void return. First, it converts the time in milliseconds to microseconds using fixed point math, and also included a scaling factor to account for the for loop overhead. Inside the for loop, it simply executes a no operation instruction. I tested this function using my logic analyzer and adjusted the scaling factor to get the spin lock delay time close to the requested time in milliseconds. Gotcha number 2. In episode 13 in this series, I used a 4 MHz main clock and a 1 MHz SPI clock to send a single byte. However, in this project, I was sending 2 bytes and found that the host device's SPI clock was too fast for the client to wake from sleep, catch the first byte and process it, and try to catch the second byte. The solution was to slow the SPI clock down to 250 kHz, which gave the client time to receive and process the first byte and be ready for the second byte when it arrived. If you have made it all the way to the end of this series, congratulations! You have built up a group of bare metal AVR libraries and built a complex low-power project using 2 microcontrollers, all while learning to navigate datasheets and relevant tech briefs. Thanks for watching.